So in the last several weeks, we have talked about the sequences. And the sequences, a very important property of all the sequences, and no matter how sub-sequences it is called a convergence. And but also from another aspect, like sequences is just a small subset of functions, which all the sequences have one property, that is all of its domains is natural number, the n. But for functions, it cannot be only n. It can be, well, it can be all the real numbers. Okay, so we'll start talking about the general functions starting from today. And the important property of functions is continuity, which is very similar to the convergence property of all the sequences. So let's make the transformation from the sequence to function starting from today. Okay. So for sequences, sequences are functions with real values, but the real values means in its range, it's real values, but the domain is a set of natural numbers. But from now on, when we talk about functions, remember we talked about functions in lecture 5, which is a domain to range, and range can be R, can be all the real numbers. We assume that its domain D is any general subset of R. So from now on, we'll always talk about the function in the form like going from D to R, and D is the domain. But here, D is any subset of R, or we can write D is a subset of R, something like that to indicate it. Okay. And just like the convergence for sequences, an important property of the function is continuity. So let's first define its continuous. So what is a continuous function? So maybe you have learned from before, like if you see a sequence like that, it is continuous, right? And a sequence, if a function looks like that, and yeah, and it has missing some values and going like that way, it is not continuous. Or there's a value here, this is empty, and it jumps here, it's not continuous. Or a function going like that, and here it has a asymptote. Well, we know these three forms, 1, 2, 3. Those three forms are not continuous, but that is not general enough. It is, you can always give different examples of how not continuous a function can be. So that is not, I don't know. I personally, I'm not satisfied with that definition of what is continuous. So that continuous can be generated from convergence or not of the sequences. So always, just like what we talked about natural numbers, we can say natural numbers are 1, 2, 3, 4, and it goes on by adding 1. But that is not very interesting to say about the natural number, because maybe how we know it's 1, why is starting 1? So we say, well, the natural number is the smallest intersection of all the sets of the inductive sets, right? So that is the real definition for the natural numbers. So for continuity, we'll define it in this way. So first, we are only talking about functions. So functions is said to be continuous at a point x0. So which means like D can be some, for example, if it's a one variable function, which is what we talk about in this section, is only one variable, which is x. Okay, and the function, it can have a range, like this is the range, this is D of the function. And the x0 is just one point, arbitrary point in this D, in this domain, can be any point. And we say a function continuous at this point, which means like, well, it goes through this point and it's continuous. Okay, so that's, we define, we're not saying the function is continuous everywhere. We just care whether this function is continuous at x0 or not. And this type of continuity, we say it is point-wise continuous, because it is point-wise, we just consider one point, right? And later we'll talk about more about different types of continuous, like the uniform continuous and some other type as well. But here, our continuous definition here is equal to the point-wise continuous, or we can write it out. It's called point-wise continuous. Okay. And that is to say, what is point-wise continuous? So for every sequence xn that converges to x0. So imagining like a sequence, this is a real number line, right? So we can generate a sequence xn like they are going closer to x0. They're going this way, and it will converge to x0. If you still remember convergence definition, that means like for all n greater or equal to n, then like probably n1. So because n is a natural number that denotion. So for all of that, then like xn minus x0 is smaller than delta, maybe delta, yeah, or epsilon, and for all delta greater than 0. So that is the convergence meaning, right? So for all of the xn converges to x0, then all of the fxn, which is here, this is xn, and this is fxn. The fxn, what its property must have is like they are convergent to this point, which is called fx0. Okay. So that is the pointwise continuous definition. And well, as we say, it is pointwise. It is not meaning the function is continuous at all in this domain. So how can we say a function is continuous in this domain? Well, we can say if like the function f going from D to R, if it is continuous at every point in D. So no matter what x0 we pick, this condition here, the convergence condition is always satisfied. Then we say, well, f is continuous in D, or the function itself is continuous because it continues at every point in its domain, right? Okay, so this is the pointwise continuous definition. And it might be, yeah, it might be a little bit hard to understand it from the paper. Like why we can say if it's a convergence for its image sequence, then it must be continuous. So continuous from its literally, it means like the function doesn't interrupt. It always goes smoothly, right? And or maybe not go smoothly. It goes. This is also continuous, but it must be connected. And like in this point, if the x is going very close to it, and fxn, if it's not going close to it, what will happen is like it will have a gap, right? If it's not smaller than every delta, like indicated here, if it's not smaller than every delta, it must be greater than some delta, and this gap is some gap smaller than delta, and this will occur, right? So yeah, so that is the understanding why the sequence we can use the sequences convergence to define functions continuity. So this is the first point we bring out. Okay, and we'll see some examples after we see that definition, so it's better to understand. So the first example is like for all of the x in R, which is an f, the function is defined as x squared minus 2x plus 4. So it is a polynomial, and the domain is all of the real numbers. So the question asks like prove or disprove its the continuity. So this function is a polynomial function, and we want to show and we want to guess whether it is a continuous function on all of the real numbers R, or it is not a continuous function. But no matter what we guess, we have to prove our guess. Okay. So we can first draw a graph of this function. It's a polynomial function, so it's usually looks like x squares look like that, and minus 2x. So probably and plus 4. So it probably looks like something like that. Okay, something like that. And polynomial function always is connected at a point. So it is, we will guess, well, it's actually continuous. So how to prove it? How to use our definition of continuity above to prove it? So first, we want to find the x0 in the R. So for every arbitrary x0 which satisfy, when we say arbitrary, it means x0 is not defined. It can be any x0. So if we can use for all x0 to prove it's, well, it's continuous at x0 this point, then every point in real number is continuous. So that's why we say it's arbitrary. We use arbitrary to prove this fact, like continuous at every point in domain, or here domain is R, right? Okay. And because the definition uses the convergence of sequences, yeah, we just want to define an arbitrary real value sequence as well. Like we just define xn that converges to x0. And what we want to show is its image, the image sequence fxn also converges to fx0, right? So that is, if that can be proved, then it is continuous. So because we already know, we already defined that xn, the sequence converges to x0, then, well, we can use then we can see here, this is what we want to find. And actually, fxn is equal to, by this definition, we can find out this one, right? And this equal sign, we use the linearity of the convergence. So x and 2, we can just separate them out. And 2, which is coefficient, we can drop it out. And plus 4, and we can also drop it out. So it becomes this one. And then I think that in the 2 lectures before, we have also, beyond the linearity of the convergence, we also studied, we also give a give a proof of why a polynomial, like a polynomial sequence, is also convergent. So if xn is convergent to x0, right? And then xn to the power of 2, which is a polynomial of xn, and it is also convergent to x0 squared. So this one, it becomes this term, and this term becomes this term, and this term becomes this term. And well, what's that? It's just fx0. So we have done the proof. So which means fx here is continuous. Absolutely. And so you can see, generally, it's very easy to prove whether a function is continuous or not. We just want to first find the arbitrary point at x0, and then to find to define a xn, a sequence converges to x0, and then to try to prove this thing, the image of the sequence is equal to fx0, right? So if all of that satisfied, then fx is just continuous, as we found out. Maybe we have a gap here. Maybe it's not, because it's already arbitrary x0. So this is why we say like arbitrary x0 is so important here. All right. And so at first we see an example of why the x how to prove a function which is continuous, and then we have to show a function, or how to show a function that is not continuous. So we'll bring a new definition here, which is called Dirichlet function. So Dirichlet function is a special form of an indicator function. So remember, we have talked about the indicator function, which is a binary result, like fx is equal to 1 if some condition is satisfied, and is equal to 0 if some condition doesn't satisfy, right? So here, in the Dirichlet function, the condition is whether x is a rational number or not. So if it's a rational number, it's 1, and it's not a rational number, then it's 0. So this is our definition of the Dirichlet function. So every time later you see the jargon, okay, you talk to some mathematician and you say, so let's use the Dirichlet function. Or what about Dirichlet function situation? Is that a open set or something? Yeah, some people may say that, and you will realize, wow, the Dirichlet function is just this one. It's not some like very complex very complex model. Okay, so is Dirichlet function continuous? It's a good question to ask, because we can roughly think about how it looks like. So there are some rationals, which is 1, right? And all of the irrationals in between is 0. So it doesn't look like it's continuous. It's not continuous at all, because the gap is 1, right? The gaps between them is 1. So that's our guess. And then we have to try to show it's actually not continuous. So remember, when we want to prove a function that is continuous, we define a sequence, and then to show, well, the image of sequence is actually convergent to that as well. So we will say, so here, so why we not just pick like a counter example, a counter situation that is not work, and then the special case doesn't work, so it does not work at all. So we just select x0. We just show that at a certain point, that the function is not continuous, then we can find out, well, because remember here we say like a function is continuous, it must continuous at every point. So if we use the contrapositive ideas, if at a certain point not continuous, so the function is not continuous. And the point we pick is x0. X0 is equal to 0. This is our this is a special case we want to show. And because like the 0 is also a rational number, so fx0 or f0 is 1, based on the Dirac function's definition. And because of the set of irrational number is sequentially dense. So this fact is based on the sequentially density, the theorem of sequentially density, which means like all the rational numbers or irrational numbers are sequentially dense, which means like every number that can be obtained by a sequence of rational numbers or irrational numbers and converges to that point. So there exists an AN, and AN is a sequence of irrational numbers which belongs to this set, and the limit, and it converges to 0. Okay, so this is a very important fact that we use the sequentially density property. So what's the result? So because AN, because like we define AN, even AN is convergent to 0. So we say, well, it's convergent to 0. And what we want to show it is not continuous at a point, which means like even it's like convergent to 0, but its image is not convergent to f0. And f0 is 1, right? But FAN, every AN term here, because it's in this set, it's not rational, so it must be 0. So it will be a sequence of 0, 0, 0, 0, 0, 0. And so the limit will be 0 again. So the limit of FAN is 0, which is not 1 and not f0. So which means like the Dirac function is not continuous because it fails to be continuous at a special point 0 here. But if you are interested enough, you can later show that every point, not just consider a special case 0, but any point in fx in the Dirac functions domain, which is R, and every point is not continuous at all. And this can be shown by separating ideas. If x0 is a rational number, if x0 is an irrational number, and to show like every rational, irrational case is all not continuous. So then you can very confident to say that it is not continuous at all. Even a small piece is not continuous for Dirichlet function. Okay, so now I think we have get an idea of how the continuous working. So later we'll move on to the operations of continuous functions. I think this part we have talked about the operations of functions before. So I will quickly go through it, and then we'll talk about the operations of continuous function. So the definitions, some definitions are here. So fx and gx, they are two functions, and some, if we see notation of like f plus g, what it means is for all of the x in the domain of the how to say union, maybe union, like because if the outer union is defined to be 0, if it's out of the domain. So if it's in the union of these two domain, then this will be the plus, and fg will be the value of each of the x product. And this one a little bit special, but if given like gx is not equal to 0 in this domain, then in this like the union of the domain, then f divided by g is defined by their each of the functions value divided by g, f divided by g's value. Okay, so that's the definition. And then, well, we're going to continuous cases. So now suppose f going from d to r and g going from d to r. Okay, so now their domain is the same. They're continuous at x0. X0 is a point in d. Then f plus g, f, g are all functions going from d to r. This is because we have studied before, like a function going from d to r, and summation, their domains overlapped. And what about its multiplication? And you can only pick value from them. So their domains still the same. And they are all continuous at x0. And for the division, if g is not equal to 0 for all of the x in this domain, and f divided by g is also continuous from D to R. Okay. So this is some property of the property of continuous functions operations. And the theorem given that following, which is become more general, is like any function in the form of a polynomial is continuous. So remember we have an example here, like this fx, this is a polynomial, and we have proved it's continuous. So this is a special case, but generally it is all of the polynomial functions are continuous functions, and this can be proven very easily, as it suggested. If you can use the convergent sequence polynomial property, we can do that. And give me a little bit more detail. Is like you can always pick a sequence xn that goes to x0 in that domain, in the domain you selected, and you will perform this one. You will perform this for every polynomial. And because the polynomial property of the convergence, then this one is always convergent to that one by going from, especially from this step to this step, and you will done that very easily. Okay, so from now on, we have studied the theorem. So anytime we met a polynomial function, we can directly say, well, it's continuous. And another corollary based on that is like if P1 is a function going from R to R and P2 is a function also going from R to R, and they're all polynomial functions, then their quotient P1 divided by P2 is going from D to R or R to R. Like here, we might, because P1 is going from R to R, P2 is going from R to R, and this one might be, well, going from D to R, which is like when P1, P2, D is the region of when Qx or Q is equal to Qx equal to P2x, when this is not zero. When this is not zero, and D is the domain that satisfy the quotient. And the quotient will also be continuous. Why? Why? Because it's the quotient property of the continuous functions, which is just above. So it will be continuous. So this is the idea here. So here we talk about like when gx not equal to 0 is denominator function not equal to 0, then fg continuous, then this division is also continuous. So here p1, p2 polynomials, and from this theorem, polynomials are continuous, and the q and when p2 is not equal to 0, and their quotient must be not equal to continuous. Okay, and the last property regarding continuous function is called a composition property. So composition function we have studied before. It's like function f and g, and with fd, f is going from d to r. So maybe we can spell d going to r, right? And g is going from e to, this is f, this is g. It's going from e to r. It may be onto, maybe not. However, like the f, this one will go to a smaller subset of e, which is called the fd, right? So this one is fd. Maybe we'll draw a better graph here. Okay. So here is d. D going by f, going to fd, which is its image set, and is contained in E, which is the domain of G, and G goes to some R, and this will be a very large set, but which I just draw it very small, so it might be so this is R. Okay, so it's so when we're using this kind of line, we say it is not bounded, so R can be very large. Okay. And then it's composite function. This is a composite function written by g, f, And if the variable is x, it's writing this form. All right. So we say like if g and f, they are both continuous, then this function is also continuous. So that is our statement for this property. And then we'll give the proof for this one. Okay. So when we are proving the continuity, we first generate arbitrary sequences. We just define sequence an in the domain D that converges to x0. And because is a continuous function, right? Both f and g are continuous. So because f is continuous, its image is convergent to that as well. So an converges to xn, fan converges to fxn, and fx0 is belong to the set of E. That is because all of the FD, all of the FD, no matter what point is choosing in D, it's a subset of E, right? And x0 is inside FD, so it must be inside E. So that's the logic here. All right. So then because G is also continuous, so using the same logic, we can easily find out like because Fan is in E, which is and that is because like all of the An is a subset of D. An is a subset of D. So Fan is a subset of Fd, which is E. Same, very similar. So which is convergent to Fx0. Then for continuity of G, so GFan will convergent to GFxn, which is the composite of GFx, which is here. And these two, maybe forget a bracket, but these two is the same. So for all of the sequence an in D, which is convergent to x0, what we can find out right now is like the GF composite an. This one will converge to the GF composite at x0. So in this case, where implies like the GF is continuous at x0, right? And because we pick the x0 arbitrarily, it's any point at x0. So that means like the composite function is continuous at every point in its domain D. So the statement is done. Fg its domain is D, so it's continuous at every D. And because the x0 is picked. Okay, so there's two different situations. When x0 is first picked, then if we only want to prove like the composite function gf is continuous at x0, then we're not able, but we are not required to show that we just pick a random x0 because x0 is already given. However, if we want to show like the composite function, this one is continuous. If this function want to show is continuous in the range of D, then we have to pick a random x0 to start with that proving strategy here again. Okay, so that's the first part. That's how we say the definition of the continuity. We use the convergence of sequence to prove it. However, there's also another type of continuity. It's very worthy to talk about. It's called the epsilon delta language for continuity. So the continuity is the same concept, but it can be explained in two separate cases. So what about the epsilon delta language? We have been very familiar with the epsilon language in like in Archimedean theorem and in the sequence convergence. But now we have added a new small positive variance here again. It is delta, and delta we can also understand like delta is very close to zero, but it's positive. So for the epsilon delta language of continuity, where it is defined in this way, it defines like for all functions f going from D to R, such that D is a subset of R. It is said to be pointwise continuous at point x0 if this statement is satisfied. So here, here again, like the continuous, we can say continuous for now because the pointwise continuous is the only case of the continuous we are studying about. However, if we like after the next lecture, we have encountered a uniform continuity, and we must say it's pointwise continuous. So I would say it's a good habit to start using the correct jargon in mathematics, which is the pointwise continuous. Okay. So it is pointwise continuous at f0 if this one happens. So what is this one? It's interpreted as like for all epsilon greater than 0, there exists a delta greater than 0 such that for x in D, which is its domain, and if x minus x0 is absolute value is smaller than delta, then fx minus fx0, their absolute value is smaller than epsilon. Okay, I'm going to use a graph to show graph to see it. So in this graph, you can see like what this statement. It may look very complex because it used 1, 2, 3, 4, 4 layers of the 4 layers of logic. So what does actually mean? We are interpreted from outer to inner. So it means like this value is epsilon. So yeah, so here is the center line and will be a symmetric band, symmetric width. This is epsilon, this is also epsilon. And it's just like for like, if we can pick a very small epsilon here, we can pick a, just imagine like this is already small enough. And then what happens is like there must exist x minus exists delta such that like x from this interval, this is x0, and this is also the width of delta. Like, and the delta, what in this range is like, if this one, if the x here must be very close to x0, and then fx well must be also very close to fx0. So after we have talked about so much, so this is the definition of the epsilon delta language for continuity. And what it fails to be correct is like, let's give you a condition like it fails. It might go like that. So imagining this is not connected. It is going from like, it's going from here and it jump to be here, right? So now we can say, well, from visually, it is not continuous because there's a gap. And why this condition doesn't satisfy is like, well, for all of the epsilon greater than 0, and epsilon can be slightly smaller because it's for all. So this can be also epsilon, right? And however, for this kind of epsilon, or yeah, or for this kind of epsilon, an interesting case is happening because like for all of the, no matter how small the delta we pick or how big the delta we pick, it doesn't matter. But for all of the x in this range, like for example, this is range, right? This is the delta range. And we can say, well, the range is here, but for all of the x smaller than like within the range of the delta from x0, no fx is in the range is smaller than the gap of epsilon, so it fails to be continuous. So it must be in this case that we're gonna say like for every delta that is very, very small close to x, and must be some fx that is very, very, very close to it. And we can also give a sequential example of it. Like, so if it's a gap like that, gap smaller than what we had before, if this is a gap, then what it's saying is like, if we pick a, like if we, no matter how small the, maybe delta is very small, very close to here. However, well, let's say we go in this way, it doesn't matter and we can still pick an epsilon like here. Epsilon can be very small as well for all epsilon, so epsilon can be here. And then we can not find, then like there's some x here, it's going to this value, and it's, yeah, it just go beyond epsilon because the value is here, but epsilon is here. Okay. So like verbally from English literature, we can say for symmetric interval with width 2 epsilon, which is we discussed here, 1 epsilon, 2 epsilon. Okay. About the line y equal to x0, which is this line. There exists an interval here, right? This interval is this interval centered at x0 of diameter 2 delta, and this is 2 delta. And the restriction of f to this interval must lies in this span. So must lies in this span. And as the case we studied before, the value goes here, so it's not within that, so it's not continuous. Okay. Okay, so let's view some examples about this new definition, the epsilon delta definition. So first, let's see the example. The function fx equal to x to the power 3. This is a polynomial function. So based on theorem before, we already know it's continuous, right? So now we're going to show why it is continuous. So yeah, you can just say like, because we say x to the power 3 satisfy the polynomials property, so it must be continuous at any point, even at x0 equal to 2. But this is not what we want to do here. But absolutely, you can do that in your homework, in your assignment. Is totally okay. But here we want to use the epsilon delta language to show, okay, this function is continuous at that point. All right. So, so for proving that, first we want to satisfy, we want to set up some assumptions, which is first of all, like for all of epsilon greater than 0, we want to find delta, which is larger than 0, such that if x minus 2 is smaller than epsilon, because 2 is x0, then its image fx minus fx0 is smaller than epsilon. So this is what the statement 1 here. It's just repeat the definition of the epsilon delta language of the continuity. And then one surprising fact is that by triangle inequality, x3, x to the power 3 minus 2 to the power 3, which is 8. This one is equal to this one, or we're just separating it out because this is, okay, so maybe we need one more step, like x, because x minus 2 times this one. This is using the, what formula we use is the, I forget its name, but it's called a sum of the square formula, maybe. So we can reach this form, and then we can find, what can we find out is like this is a absolute value outside, so we can do the absolute value separately, and this is equal to x plus 2x plus 4, right, times the absolute value of x minus 2. And this one, this is equal, but this one we can just write equal as x minus 2. It's totally fine. But for this one here, it will be a little bit tricky because it's an addition of three terms. So using triangle inequality, this is smaller or equal to the summation of each of them plus 2x plus 4, right? So what this is why we get the formula here, right? And so what's the continuous? So what's the next one? So because for all of 1 smaller than x smaller than 3, so here maybe we already define interval is like from 1 to 3. So because x0 is 2, 1 is 1 distant from 2, so the epsilon is 1, right? So it's from 2 minus epsilon to 2 plus epsilon. So this is the range here. This is the domain here. And this part is smaller than 20. And this part is, so what this part is, because is in this form, and this one will be smaller than 1. This is smaller than 20. So this one here, this one, because so like this one is smaller equal to this one, but this one is smaller than 20, so it must smaller than 20 times x minus 2, right? This is the absolute value getting from here, and this is we calculate this part as smaller than 20, so we get the result here. All right. So now we are moving at this step. So now we'll find out maybe the delta we want to define here is not just 1. It is very interesting to define like delta to be the minimum of 1 and epsilon divided by 20. So why this is important? So why we want to define this one? Because what we want to prove finally is like this one. So this term here, well, this one, if this one's smaller than epsilon, and not this one smaller than epsilon, it's like what we want to prove is that if this one smaller than epsilon, right? As in the statement 1 before, and this term, okay, so this term well smaller than epsilon. So epsilon is smaller than, so what we want to find is epsilon is smaller than 20 delta. So which is also mean to say like delta is larger than epsilon divided by 20. So we just want to say, well, why not just define delta as the minimum of 1 or epsilon over 20. And why we need 1 is like if it's greater than 1, it's delta. If this term is greater than 1, then this condition will fail to satisfy. So we want to make sure like delta is in the range. It's the number of epsilon divided by 20, but it will not be greater than 1. But you may also want to say like, well, if we directly define delta as 1, will this fact be disappointed? Will this be unsatisfied? Well, it is impossible, because when we are defining 1 and epsilon, like when we are choosing the minimum of 1 and epsilon over 20, the cases if we will only choose 1, given like this one is larger than 1, right? And so this one is larger than 1. So even we pick 1 as our like delta, it's still satisfied this this condition. So it's totally okay. All right. So after we defined the delta here, it goes very straightforward. So x minus 2 smaller than epsilon, smaller than the delta, and x to the power 3 minus 2 to the power 3. The image is smaller than, yeah, it's smaller than 20 times delta, and smaller than 20 times the epsilon divided by 20, because can just mean like, because this one we just pick here in most of the cases. So this is just smaller than epsilon. So yeah, we are done. However, let's consider like if this one is larger than 1, so what's the case? So this is 20 times, so this one here becomes 20 times 1, smaller and equal to 20. And 20 is what case? And 20 is like, it's smaller than 20 times 20 over epsilon. So in this case, it's like this is equal to epsilon. So it's still smaller than epsilon, and it's more smaller than epsilon than the previous cases. So yeah, so by summary, by conclusion, we draw here, we just say most of the cases, if we just use delta equal to epsilon over 20. But why we use the minimum here is just we want to make sure our delta must be satisfied in this range. So that's the only consideration why we take the minimum here. Okay, so this is a example that we show like how to use the epsilon delta language to prove a function is continuous. And also we can also use it to prove a function that is not continuous. So let's say let's define a function like that. So this is not a Dirichlet function, but it is a, well, it is an indicator function, but it's not a traditional indicator function. It's a transformed indicator function because this is no longer 1 and 0, but it becomes minus x and x minus 1. Okay. So in this case, like fx is equal to or minus x if x is smaller or equal to 0, and this one is equal to x minus 1 if x is greater than 0. So I'm going to draw a graph to show it. So when x is smaller or equal to 0, it's negative x, which is in this form, right? And when it's larger than 0, it's x minus 1. Okay, so this is 1, this is negative 1. So that's our function fx. Then we'll show like this is not continuous at 0. So obviously, well, from the image we can see there is a gap of 1. So absolutely it's not convergent. But we'll use the epsilon delta language to show it's not continuous. So we can select the epsilon because we are proving it's not continuous. We'll just do one counterexample. We can pick epsilon to be any value, but here we just pick it to be 1/2. So epsilon, we pick it here. And this is negative 1/2. Okay. So this is here. And what will happen is like, well, no matter how small the delta is, as we illustrated before in the previous graph, no matter how small we pick it, there's always like, if the sequence like the value going from this way converged here, but the value here is always beyond this range, right? So yeah, so it's not continuous, as we can give a counterexample of it. And this fact is stating can be formally stating as here. So like for all of x smaller than belongs to 0 minus delta, 0 plus delta, no matter how small delta is, fx minus f0, this function is equal to fx minus 0 and is equal to fx. And fx, well, when we goes from the fx from the yeah, so when we pick fx, remember from the positive direction for all of the delta greater than 0, and we can pick a delta divided by 2. This is a sequence, right? So this is a sequence that makes sure it is in the range of minus delta to delta. However, this one is in this range. But the case is like f delta divided by 2, this goes to 0, which means like this term is also go to 0. And f0, when it's slightly more positive, it is negative 1. And this is go beyond this equal to 1, which is larger than 1 or 2. So yeah, so this function defined here is not continuous. And also like when we have talked about the two criterion to prove a function is continuous or not. For all of the function going from D to R at a point x0, the two following statements are equivalent. So which means like if we can use if we can use this one to prove that the function is continuous, and we absolutely can use this one to prove a function is continuous. They're the same statement. They're logically equivalent to each other, which makes sense because if you have two criterion for whether function is continuous or not, but finally we find like they're actually different. Some function can be satisfy A but not B, or B but not A. So which make sense like one of them must be wrong. So this is an interesting theorem, and it's a very important theorem for understanding the connection between the epsilon delta language and the sequence convergence. So we'll prove like when we assume A hold, and we'll prove from A to B, and then we'll prove the converse way from B to A. So first, let's just assume like A is correct. And we just want to show like B then we want to show B, right? We first in this one, like first we assume A is correct, and we'll prove B. So proving B, we can use the contradiction. Well, we can prove by contradiction, which means like we first assume B doesn't hold because there exists a epsilon 1 larger than 0, but we cannot find a delta larger than 0 that B holds. So it's a contradiction. And what this means is like for all like natural number xn in the like in the range of D, and xn minus x0 smaller than epsilon, smaller than delta, and delta here we define like delta is equal to 1 over n. And this is smaller. However, this is not smaller or equal to, this is not smaller than epsilon, but it's larger than equal to epsilon 1. Okay, so this two line is our assumption here. And then we'll use our condition A to show like this is impossible. So why is it impossible? Because I also define sequence x and in D, and each term is equal to xn, which makes sense. We just plug in every xn into the sequence. And because xn minus x0 in the condition here is smaller than 1 over n, and like when we first studied the sequence, we know 1 over n, this sequence is converted into 0. So xn is converted into x0 because xn minus x0 is smaller than 1 over n, and as 1 over n close to 0, and this one will be the same, so it's converted into x0. And remember, like we have known like A is true, so if xn is equal to is converted into x0, then it's f xn is also converted into f x0, which contradicts to the previous finding. We have found this one here, right? It's go beyond delta 1, the epsilon 1. However, if this is the case, then like this means like for all of the epsilon 1 greater or equal to 0, greater than 0, and f xn minus f x0 must smaller than epsilon 1 for all epsilon 1 larger than 0. So this is the case we deduce from the beginning, but this is our previous assumption. So statement B cannot be not true. So statement B has to be true. So we have proved from A to B. And conversely, it's very similar too. So suppose B holds and we can define the sequence X and in D, then now our situation here is like we assume B is true, and we're going to find out whether A is correct or not. And when we are finding whether A is correct or not, we can first assume this is correct. There is a sequence xn in D, and the xn is convergence to x0. And the only thing we want to find out is the question mark here, whether its image is convergent to the image of x0. Okay. Okay, so let's start with that. So yeah, so here we already assume like the xn is convergent to x0, which is in the domain of D, and this is important. So which implies like for all of the epsilon larger than 0, and for all of the n go beyond the index n1, xn minus x0 is smaller than epsilon. So this is a definition of convergence we use here again. This is a definition of convergence, and because B is correct, and because B is correct and this is correct, so f xn minus f x0 must be smaller than epsilon for all epsilon larger than 0. And this is because like for all of the n larger than the index n1. So this is additional condition. However, that doesn't matter because the convergence also need that condition. So this one here is just indicates like the f xn is image sequence is converted to f x0. So now we have proved like A is true. So B from B to A is also proved. So previously we proved A to B, and here we proved from B to A. So now we have done all the proof for for the if and only relationship. So these two statements logically equivalent. All right, so the previous epsilon delta criterion for domain is like we have to pick a fixed x0, right? Because when we discuss here, we must say, well, it is pointwise continuous at point x0. So the x0 is a fixed value. However, when we consider a domain of some functions, it might not be that fixed because like when we give a function, a natural function, like a common case function going from D to R, uh, and x0 is just an arbitrary point in it. So maybe we can pick two such x0. One we define as u and another we define v. So now the situation becomes like that. This is x and r, and this is d inside. And we can pick a point x0, but we can also pick u and v. And u and v, they can be any point as well. However, like the between u and v, the distance can be long, right? It cannot be very, very small, but it can also be long. But the previous cases when regarding a sequence is like because it's convergent to x0, so go beyond a certain point, x is very close to x0. But here, u and v can be very, very far away. And for all of the u and v, like if they are close enough, then the function fu and fv will also be close enough, like in this function. And if satisfy that condition, we'll say it satisfy the delta epsilon criterion for domain D. And this kind of continuity is no longer pointwise continuity because it has how to say it has far more it is no longer we pick a point, so it's not pointwise. And this kind of like if we can pick 2 point u and v in that, and it can be very far away, but still satisfied this even then relationship, and then we'll say, well, it is called uniformly convergent. And for uniform convergent, we'll talk about in the next one. And the next one we'll also bring about probably it's called the intermediate value theorem. Yeah, and that is very useful for calculus.